So, we were talking about methods for immobilization of enzymes. We have been talking about methods for immobilization of enzymes, and we have in our earlier meeting have discussed the first method called adsorption, and this method includes various combination of methods including physical adsorption, ionic binding and metal salt linkage. It also involves involvement of a carrier matrix, and sometimes these are known as carrier binding methods. The other methods that are known and available for immobilization of enzymes are cross linking, covalent binding, entrampment within a matrix. It could be a gel, a fiber or a microcapsule, and finally the containment of soluble enzymes in the ultrafiltration reactors. They are the whole variety of immobilization method, out of which we will be talking in a short while about the cross linking methods. The cross linking methods essentially involve intermolecular cross linking of enzyme molecules in the presence or absence of a solid support. Now, I would like to make very clear the phrase presence or absence of solid support. Now, while basically initially the enzyme molecules are interlinked through a bifunctional reagent between some of the functional residues on the enzyme protein itself. The method produces a 3-dimensional cross-linked enzyme aggregate. That means 3 or 4 or more enzyme molecules aggregate together through a covalent linkage mediated by a cross-linking agent, which is usually a multifunctional reagent, and therefore the enzyme molecules form an aggregate that are insoluble in water, and they retain the catalytic activity. That means the intermolecular cross linking between the enzyme molecule should not involve the cross linking the catalytic functional group required on the enzyme molecule. Now, a characteristic feature of this method is that ultimately when you get this material, you end up in a gelatinous mass. That means you do not get a particulate matter, while the enzyme molecule is aggregate and come out in the form of a precipitate, they are gelatinous mass, and obviously in the case of while they are used in the enzyme reactors, they do not offer a good flow property in the reactor, and therefore they are not a very desirable kind of a material which can be processed in enzyme reactors. To overcome this, very often they are used in presence of a solid support. And as a matter of fact, if you recall, when we talked about adsorption, we mentioned that adsorption being a reversible process, the immobilized enzyme preparations that are produced by adsorption are usually do not have very high or long operational stability. To enhance the stability of the adsorbed material, very often adsorption is combined with cross linking, so that the cross linking is carried out in the presence of a adsorbate, a matrix on which adsorption can take place, and then the cross linking is carried out so that you get a very stable immobilized enzyme preparation, which also has the morphology of a particulate matter. If you recall the method of immobilizing enzymes by adsorption, one of the major drawback of the adsorbed enzymes is that they do not possess a very high operational stability. Now, to overcome this problem, if the adsorption process is coupled with cross linking of the enzyme, so that ultimately what happens that each of the enzyme molecule is here present is supported on a matrix and also cross linked to each other, so that it forms a multivariant multivariant force by which the enzyme will not be desorbed, because it is now covalently linked to each other, and the advantage will be, and the other disadvantage of the cross linked enzyme, that is gelatinous morphology, will also be removed, because the immobilized preparation, cross-linked preparation in the presence of an adsorbent will have the morphology of the carrier particle. The adsorbent whatever we have used, that morphology will be available, and thereby one can get a much better preparation which can be used in reactor systems. Now, a large number of cross-linking reagents. Now, one of the important thing what we should recall is that now these intermolecular cross-linking require certain very reactive reagents, so that the functional groups of the enzyme can covalently bind under mild reaction conditions. Mild reaction conditions, again I will have to repeat, under those conditions in which the enzyme does not lose its conformation or the functional reactivity, and now for those purpose we need certain reagents which are multifunctional and also very reactive. Some of the typical reagents, although it is not the complete list, but some of the typical reagents which are commonly used are diisobenzidine. It has two functional groups and 1,5-difluoro-2,4-dinitrobenzene, two nitrate group and fluoro groups, then trichloroastriazine, hexamethylene diisocyanate, and of course the most commonly employed cross-linking reagent over the years has been glutaraldehyde. The most commonly used method of cross-linking the enzyme molecules is by the use of glutaraldehyde, which possesses two aldehyde groups separated by a hydrocarbon chain, the 3 CH2 groups, and this reagent is very commonly used for all cross-linking experiment, even routine as well as for practical. Now, the reaction that it catalyzes, the glutaraldehyde is composed of two different reactions. One is the glutaraldehyde solution. Essentially, when you store it, it is present in two different forms. One is the free glutaraldehyde, a single glutaraldehyde molecule which contains two aldehyde groups separated by 3 CH2 groups, and also it also occurs in the form of a dimer, in this form, in the form of a dimer in equilibrium. The two forms are present in equilibrium. Sorry, this also we should include. It is also, so it is available in this form as well as in this form. Now, from the two forms, it gives you two different kinds of cross-linked enzyme preparation, while in the case of the first, the monomolecular glutaraldehyde residues, they give you a cross-linking reaction between the enzyme molecule, particularly the amino groups of the enzyme molecules are involved in cross-linking, and you get a chain of amino groups, chain of the enzyme protein which gets aggregated and gets precipitated. On the other hand, the dimer of the glutaraldehyde forms a addition conjugate and along with the enzyme, and it again gives you a precipitated mass and this addition compound, and both the forms remain catalytically functional. So, on storage essentially the concentration of this dimer increases. So, very often, but the only difference will be that the reaction conditions that have to be employed. When I say reaction conditions, I am referring to the concentration of the glutaraldehyde, the ratio of the glutaraldehyde to that of protein, the time of reaction, the temperature of reaction. They will vary in the case of two reactions. So, depending on the age of the glutaraldehyde or the storage conditions of the glutaraldehyde, we may have to, and very often it happens that some standard conditions given in a book do not exactly replicate in a laboratory experiment, mainly because if the glutaraldehyde solution is available of different age where it has undergone this dimerization, it will behave in a different way in the product, but both the products are essentially cross-linked preparations and are useful. Now, as I mentioned that the cross-linking method also must involve or identify certain optimum conditions for the reaction for cross-linking, and the optimum conditions depend upon the balance of parameters like concentration of the enzyme and cross-linking reagent, pH, ionic strength, temperature and reaction time. In out of the large number of studies that have been carried out for cross-linking, particularly with glutaraldehyde, usually a protein concentration of 50 to 200 milligram per ml, 50 to 200 milligram per ml is the usual range in which we operate for cross-linking operations. The glutaraldehyde to protein ratio is also used as about 10% weight by weight, and glutaraldehyde concentration is also of course varies over a large range from 0.2% to 0.6% solution. That means a very dilute solution of glutaraldehyde is required, and at a ratio of about 1:10, that means 10% of glutaraldehyde on the basis of protein content in a mixture, and that is allowed to react for time period ranging from say about 1 to 3 hours to 24 hours. Again, this time period is dependent on temperature, because in depend on the temperature requirement is linked directly with the stability of the enzyme. Some of the enzymes which are fairly stable, thermally stable, they can withhold the room temperature and you can carry out the cross linking, say for example in 1 to 2 hours, whereas certain other enzymes which are very sensitive to heat, they require to be reacted at 4 degrees centigrade, and then the reaction requires a time interval of at least 24 hours. So all these parameters need to be optimized for a particular enzyme system to be able to get a gelatinous mass which is cross-linked enzyme preparation. Again, as I mentioned, while cross-linking may become a useful method in the laboratory in the form of a gelatinous mass, but for practical reactor operation, a gelatinous mass does not offer you a very sort of useful flow properties in the reactor for a continuous reactor. Therefore, we usually use it along with an adsorption method. That means we take an adsorbent, along with adsorption we add or after the adsorption is over, we add glutaraldehyde to it and ensure cross-linking of the enzymes that are adsorbed in the matrix, and the cross-link preparation then provides you a good immobilized matrix for use in the reactors. Now the other method, and of course which has a very large variety, is based on the formation of covalent bonds between the enzyme and the support matrix under mild reaction conditions. The conditions of mild, the term mild again apply to the same feature, and basically because we are talking about the formation of covalent bonds between the matrix and the enzyme molecule, it brings in two major considerations. One is because of the covalent bond formation, the immobilized enzyme preparation is very stable. Usually the covalently immobilized enzymes preparations will have an half-life of few months, when operated in a reactor, and of course when stored under storage condition, it could go even for years without any loss of activity, or particularly in terms of half-life. But on the other hand, because it involves the covalent bond formation involves very active, very reactive reagents for carrying out the reaction at room temperature or ambient conditions, it is bound to affect the conformation of the enzyme protein. Although while every care need to be taken in covalent binding, that the amino acid residues that are involved in the catalytic function are not involved in the covalent bond formation, but still the reagents are not very specific. If suppose we take a reagent, let us say we design an experiment to bind to make a covalent binding with, say for example, N-terminal amino groups of the enzyme protein, but now the reagents which will act on N-terminal amino groups, it will be very difficult for them to ensure that none of the amino groups of the lysine are not involved, and if lysine happens to be a amino acid residue at the active site, there will be significant loss of activity. And very often again in practice, while we get a preparation which is highly stable, we also get a significant loss of enzyme activity. Almost 40 to 60% loss of activity is a very common feature in covalently immobilized preparation. But if you consider the overall productivity of the immobilized enzyme, that means the yield of the enzyme immobilization, after considering the operational stability, it still remains a desirable method. Of course, the choice of the method again will depend upon the carrier cost and the chemicals involved in the immobilization method. And one of the disadvantages part is that usually the carriers here cannot be regenerated, because the carriers are functionalized, they are attached with the protein, and when the enzyme conformation is lost, protein is still coupled to them in the deactivated form. So the carrier cannot be regenerated, and therefore carrier cost coupled with the cost of immobilization, particularly in terms of chemicals, it becomes quite high. So unless we want enzymes with a very high stability, that particularly when the enzyme cost is very high, you do not want to lose them during the reaction, such methods are not preferred. Of course, the most of the chemistry of the covalent binding is based on or has been developed on the basis of the chemistry available for preparing the matrices for affinity chromatography, because there also you couple a ligand onto a matrix by covalent binding to make a stable ligand bound matrix, and almost similar chemistry, because we have the similar functional groups available here. It could be amino group, a tertiary amino group of lysine or N-terminal amino acid groups, or a variety of other groups that are available on the amino acid all the enzyme protein, and they could be for example the amino groups of lysine and terminal amino groups, this thiol group of cysteine, carboxylic group of aspartic or glutamic acid and carboxy terminal groups, phenolic group of tyrosine, hydroxyl group of serine or threonine, it could be imidazole group of histidine. So basically the functional groups that are involved in the covalent binding are essentially same as that involved in the preparation of matrix for affinity chromatography. Almost similar functional groups on the ligand are used for making the matrices there. So almost similar chemistry is applied, excepting that in those cases our ligand is a thermally stable molecule. So you can choose your methods available for choice is a much broader choice compared to using enzymes, where the stability of the enzyme becomes a key issue. Now if you look at the covalent linkage is accomplished through functional groups that are not involved in the catalytic function, of course a very standard prerequisite for any immobilization method. Now a very important general observation is that on the basis of average composition of the proteins, that means the availability of different amino acid residues in the protein molecules and the number of reactions that are reported for each amino acids, you notice that this is a kind of a sequence. Lysine has been most commonly used for covalent binding, that is amino group containing amino group of the next, followed by cysteine, followed by tyrosine, histidine, aspartic acid, glutamic acid, tryptophan, serine, threonine and methionine as a rare case. So that kind of a series, this is based on, let us say, a large number of methods which have been reported by people in the literature, and also the average composition of the protein. This kind of a sequence is the observation which is followed. Now if you look at some general principles of covalent coupling, we can probably consider all covalent bond forming immobilized enzyme preparations on the basis of three classes of methods. The A class refers to grafting of the enzyme to a preformed water insoluble functionalized polymer. That means the polymeric matrix is already functionalized, that means has a very reactive functional group which under ambient conditions can react with the functional group of the enzyme protein and give you the product. A typical sort of reaction is shown here. A matrix containing functional group X reacts with the functional group on enzyme, and the grafting takes place and the enzyme gets grafted onto the matrix and the functional group is some other molecule is released. Another class of method is copolymerization of enzyme with the reactive monomers. That means you do not start with the functionalized polymer, you start with polymerization reaction starting with monomer and copolymerize along with in the presence of enzyme. That means essentially the some of the functional groups of the monomer and the enzyme have to be common. So that in the polymeric chain, in the polymeric network, at some places instead of the monomer unit the enzyme is inserted, and essentially you get a polymeric mass which contains enzyme molecule distributed in the polymeric network, and that kind of method. And the third and very commonly employed method is via activation of the functionalized carrier. You do not take a preformed carrier, but obviously some carrier with some functional groups, activate those functional groups by certain reagent, and then the activated functional groups or activated matrix then can react directly with the enzyme functional group to give you a immobilized preparation. And for example, indicating here a hydroxyl group containing matrix, you react with a, say for example, a bifunctional reagent. It could be, let us say, both the X and Y could be aldehyde, like in the glutaldehyde they could be different also, X and Y. You get a activated matrix, and the activated matrix then can react with the amino group of enzyme and give you the enzyme bound to it, and the ammonia can be released. So basically a variety of methods that are available in literature for covalent binding will fall into one of these three categories. Of course, I think the interesting part is that a very large number, if you look into literature, probably during first part of the 70s, a very large number of reactions have been reported for immobilization of matrix, immobilization of enzymes onto polymeric matrices by covalent binding. And of course, not that all of them are industrially useful, because sometime you synthesize a immobilized enzyme preparation because of the cost considerations or the other factor which we discussed earlier, they may not be so attractive industrially, but still the technique is available, and for some other applications probably that method might become useful. So I think just to illustrate the methods, I will just take a few examples to illustrate, and say for example the first and the simplest method is diazo binding. You get a you make a diazonium derivative of the solid support by treating the support containing aromatic amino groups. Say for example, if you take a support which contains aromatic amino group with sodium nitrite under nitrite under acidic conditions, you get a diazonium derivative of the and this diazonium derivative essentially is highly reactive and can react with a number of amino acid residues that are present on the enzyme molecule. And for example, with the phenolic group, for example, if you take this and provide with a phenolic group of the enzyme molecule, it reacts and gives you a enzyme containing an enzyme bound at the phenolic group, it can give. Similarly, it can also react with your histidine group, it can also bind to a histidine group and similarly give you a immobilized preparation with a diazonium bond.
Where does the N come from?
Pardon?
The first reaction is N2Cl.
Yes.
The reaction where does the N double bond N come from?
From the amino group of the in the case of amino group of the histidine residue.
So the first reaction with the hydroxyl group of the enzyme, where does the N double bond N come from?
Diazonium, this is a diazonium derivative. No, sorry, this is NCl. No, this is here there is an no. I think this is N triple bond NCl. Not there is already an N there, right? And diazonium derivative will have N triple. This is your N triple bond N. And similarly, it can also react with your amino group of the lysine, and again similarly give you a immobilized enzyme preparation, and that is one method which is used very commonly, particularly because its versatility. Only difference is that, for example, for the phenolic group, the pH requirement in the three cases, the pH requirement here it is alkaline 8 to 9. In the case of histidine, it is 5 to 6, and for if you consider through your amino group, the pH requirement is also 5 to 6. So basically, under controlled pH conditions, one can use different functional group of the enzyme protein depending on the amino acid groups that are available at the active site to produce an immobilized enzyme preparation by azo binding methods. A large number of methods for covalent coupling are based on peptide bond formation. Essentially, the same bond which is available in the protein molecules, and of course a very simple reaction is essentially if you take a acid anhydride that can react with the amino group of the enzyme molecule and give you an immobilized preparation with CONH enzyme and CO. Now, one of the typical factors here is that in addition to the enzyme binding, you also generate a carboxylic group, which means an additional charge on a free charge on the immobilized enzyme preparation, and this negative charge gives sometimes undesirable properties to the preparation, and sometimes it can affect unfavorably the stability of the enzyme, and to overcome this disadvantage, it is usually neutralized by some of the negatively charged species by addition of diamines. You add at the end of the reaction certain diamines, so that this amino group, the carboxylic group which is generated is neutralized and gets bound with the amino group, and the preparation is neutral in preparation.
Can't another enzyme molecule bind to the carboxylic group and form the peptide bond?
Yeah, no, that will not be peptide bond. It cannot form a peptide bond.
As in another enzyme.
It can electrostatic interaction. It can bind if you have a negatively charged protein, but it cannot form a peptide bond under the mild reaction conditions. Only at the reaction conditions at which we are talking, it will be only feasible to if you have a acid anhydride group. Simply, let us say if you simply take a carboxylic group containing matrix, put into enzyme solution, it will not make a covalent bond, because you need a activated matrix. This functional group has to be active, or the reaction should be feasible under conditions which are mild, in the sense that they usually very close to the ambient conditions, which is not feasible. yes, you are right that this this free carboxylic group will be available for absorbing some proteins which are negatively charged, and that is why it is usually followed that we try to remove this charge group so that it does not interfere during the reaction. Another method by for peptide bond formation which is very commonly employed is by the use of certain condensing reagents. You see, there is a group of reagents defined as R, N, C, N, R dash. There are two R and R dash are the alkyl residues, and now these reagents, they can combine or they can activate the carboxylic group containing matrices to give you under acidic conditions, usually pH 4 to 5, and they can give you orthoacyl isourea derivative, that is your COO CNHR NHR dash plus, now if you couple now this, if it is reacted with, let us say, amino group of the enzyme, then at pH 4 to 5 you get a preparation CONH enzyme, again a peptide bond is formed, and therefore these range of this is not really a single reagent. These reagents which are commonly called as carbonamide and are available in a whole range of these residues, these derivatives R and R dash, which also makes its solubility properties, because some of these reagents are soluble in aqueous medium, some are insoluble in aqueous medium, and you require a non-aqueous or a more non-polar medium. In fact, I would like you to look at, or I will also like to introduce you to another method involving the use of cyanogen bromide, not only from the point of view of preparing a immobilized enzyme preparation, but it also has an additional property which I would like to introduce, and the cyanogen bromide method is used in the case of carriers that have hydroxyl groups. I mean, if a typical example is your cellulose. Now, if you react with the cyanogen bromide, you get an aminocarbonic acid and this aminocarbonic acid then can react with the amino group of the enzyme to give at pH 8 to 9 under alkaline conditions to give you CHO, CONH and CHOH, where enzyme is coupled here. Now, one of the characteristic feature of this reaction, and for which it has been used and valued, is that you can adjust the distance of the enzyme from the matrix, but we often name as spacer arm. We had yesterday also discussed that in certain, for example, in the method of metal salt linkage, by repeated use you can increase the distance of the enzyme molecules from the support matrix. Similarly, here after this aminocarbonic acid complex, instead of reacting with the enzyme molecule, you can react it with, say for example, a amine hexamethylene diamine, which provides you free amino group, and that hexamethylene diamine will attach here, or instead of giving you a immobilized enzyme, you will be getting your CHO, CONH, CH2 CH2, I mean you can use any length of the hydrocarbon chain, 6 NS2 and CHOH. So you get a hexamethylene diamine derivative of the cellulose, and that where you have already separated the mate matrix by 6 CH2 groups. So therefore, in most cases where the enzymes experience steric hindrances, this method can give you a preparation whereby the steric hindrances are totally overcome, and the enzyme preparation, immobilized enzyme preparation.
How do we get at this?
Pardon? You see, as I mentioned, when you after you have treatment with after cyanogen bromide treatment, you get aminocarbonic acid, then you can react with amino group of the enzyme molecule. Now instead of amino group of enzyme molecule, you react this material with hexamethylene diamine, or for example for any matter, for any compound which has amino group as a functional group and a chain of methylene groups. So again the reaction will take place with the amino group, and the hydrocarbon chain will be inserted in between, so that your and then this amino group can be used, this amino group containing derivative can be used for immobilizing enzyme by any method which is applicable for amino group containing material. So therefore you can get immobilized enzyme preparation which is essentially free of any steric hindrance. Now the point which I would like to stress that there are a large variety of covalent bond formation methods available in literature, but the choice of the method will essentially depend on what enzyme we are trying to immobilize, because we must know what are the functional groups involved in that enzyme molecule, so that any method which is based on coupling of that particular functional group which is involved in the catalytic function must be avoided. And second thing, we have to know the stability of that enzyme, so that the reactions that we are using must also not be carried out under reactions at which the enzyme catalytic function is poor. And for example, if the enzyme is more stable under alkaline pH, then we can take a method which is based on alkaline pH, because if you find the whole range of method, you can get in the whole range of pH conditions, whole range of temperature conditions, and of course temperature usually we don't go, we can go lower than ambient, we usually do not go higher than ambient for all these kind of preparations. And the immobilized enzyme preparations, but one of the major advantage in the case of covalent bound enzymes is their stability. They can be used over a long period of time with very high operational stability, but the cost of preparation usually is much higher than all other methods. So I think we will stop at this point today.